Okay, hello everyone, and welcome to Multi-Site Data Center Solutions with VMware and NSX. So my name is Ray Budavari. I am part of the technical product management team in the network and security business unit at VMware. So that means in my job, I kind of have the good fortune to get to work on NSX and all things related to network virtualization. And today I'm really excited to cover how NSX can help address these multi-data center requirements. Because really it's good for me to move the discussion beyond NSX and product and start talking about solutions. So the first thing I want to do is start with a few questions because I'd like to get a bit of audience interaction. And this is also because I'm going to have to go fairly quickly to get through the content. It's an advanced technical session, so I wanted to cover a deep level of content, but I'm also a bit concerned that I might have been a bit overly ambitious. But we'll see how we go. So my questions are, who here in the audience has been to an NSX session, either at VMworld or another event? Fantastic. And who has hands-on experience with NSX, either through a hands-on lab or maybe a POC deployment? Okay, not too bad. How about anyone in the audience using vSphere today in a multi-site deployment? Excellent. And how about people using VMware Site Recovery Manager? Okay, excellent. Looks like we have a lot of people in the right room. That's good to see. All right, so standard disclaimer. For the most part, everything I'm talking about is available in currently shipping products, and if that deviates, I'll make sure I call that out. So our agenda today is going to cover really some of the key multi-site use cases and traditional networking challenges when it comes to multi-site. Then I'm going to provide some background on network virtualization and how it can help, followed by a technical review of the deployment options and a brief discussion on disaster recovery. This would otherwise really be a separate session, but I wanted to really clarify how disaster recovery is different to an active-active data center use case. And then hopefully leave some time for questions and answers at the end. So when it comes to multi-site deployments, we really see two main areas here, enterprise and cloud. And so I'm going to start by talking about some of the requirements that enterprises have. Plus, this slide also gives me an opportunity up here to show my Australian background in the image. So, I had to throw that in there as well. But basically, the key enterprise use cases that we see are, workload mobility across sites while retaining IP addresses, support for data center consolidation or migration projects, and these get significantly complicated, if the applications are impacted by IP or network changes, extending networks across physical sites to allow for capacity expansion or, more effective use of your data center resources across more than one site. So disaster avoidance. So by being able to support live migration of workloads, latency and bandwidth permitting, enterprises can really start to proactively respond to data center changes or resource constraints. And then disaster recovery, it's also a key requirement for enterprises. So some of the things that we typically see in the enterprise, is that they'll have a common administration across data centers, so it gives us a bit more flexibility in terms of controlling or implementing a solution down to the infrastructure layer. And typically there'll be high bandwidth and low latency in these enterprise use cases. Then the hybrid cloud scenarios, there's a few specific considerations here. So the use cases here are really around migration of virtual machines to the cloud. So going from on-premise to off-premise, and if possible, retaining the same IP address will really help reduce some of the barriers to cloud adoption and reducing impact on applications. And then there's cloud bursting, so the idea of being able to leverage additional capacity from a cloud provider to meet temporary demands, again, without needing significant modification of your applications. Now, given these cloud use cases typically involve internet or maybe WAN services, they'll be generally lower bandwidth and higher latency, and you typically will have no common administration across both locations. So the on-premise resources will be managed typically by the enterprise or outsourced, while the off-premise resources will be managed by the provider. So that means that given you're going across different boundaries, workload migration will generally be cold in these scenarios. So next, we're going to talk about some of the challenges, the traditional challenges when it comes to multi-site. So, traditionally what happens is you'll deploy your applications in the data center, and then, so we'll deploy some standard multi-tier applications over here on the left, and then you'll create your network and security services, so firewall and load balancing will be configured and tied to that location. So then if an enterprise wants to leverage another data center, generally speaking, they might want to move an application for consolidation reasons or extending an existing application. So this typically involves some challenges. Often or generally there's a change of IP addresses for the second location. You also need to reconfigure the physical network for your layer 2 and layer 3 connectivity. Then you need to somehow update your load balancer and firewall policies to make sure that they're in sync. And really this is a disruptive and error-prone process. So some of the traditional methods that this problem has been solved have involved extending layer 2 over dedicated fiber, maybe using a managed service like VPLS over a service provider's MPLS backbone, or hardware-based approaches like OTV, where we're tunneling layer 2 over layer 3. But even with these solutions, there's still a number of challenges. So these approaches have really created a high barrier of entry to adopting multi-site solutions because they're expensive and often require new and specialized hardware when your existing network and your existing equipment may be perfectly adequate for your other requirements. They introduce complexity and or proprietary solutions that require new skill sets. If it comes to managed services, often these have lead times of months from providers, so you're not exactly very agile. And really, the other key point is that these are solutions that are only focused on the network and are not built for automation. They're very targeted solutions or point solutions. So that's kind of the background and use cases. Now I want to talk about network virtualization and does it help this landscape at all? So network virtualization provides a rich set of logical network and security services decoupled from the underlying physical infrastructure. And some of the services include layer 2, layer 3, NAT, firewall, load balancing, VPN, quality of service, really all of the services that you expect from a network are faithfully reproduced in a logical space, as you can see. And this can be deployed on demand as required also. So this capability to extend layer 2 over layer 3 network boundaries that network virtualization provides can also apply across data centers. And by virtualizing these services, network virtualization also reduces the complexity of the underlying physical network. So the physical network is still critical. It's an IP transport that is needed, for reliable packet delivery. But because we're no longer exposing the virtual machine information to the physical network, we're no longer tied to a physical location either. So network virtualization also provides simplicity because the exact same tools and components are used in a multi-site deployment that you would use in a single-site deployment. It's also built for automation. It can be fully orchestrated using RESTful APIs. And finally, it's scalable. With network virtualization, our scalability is not tied to hardware limits. So, moving on specifically to NSX, there are a number of key components here in NSX that we can use to address multi-site use cases. That's namely VXLAN logical switching, distributed logical routing, distributed firewall, and also L2 VPN services. And really, a software-based solution for multi-site using network virtualization will work on top of any IP network. So it's going to provide a compelling approach compared to the traditional hardware-based data center interconnect solutions we talked about before. Also, multi-site with NSX provides a comprehensive approach through integration with compute, storage, and networking when we combine with other VMware solutions such as vSphere Metro storage clusters and Site Recovery Manager. So before I jump into the details of the solution, I think I need to take a step back and really explain the key NSX components to multi-site solutions so we can really highlight how they help in a multi-site deployment. So starting with logical switching, today most of you, I imagine, are using VLANs to provide isolation for your applications. And what you'll typically do is either trunk these VLANs to every top of rack switch and present the same VLANs to all of the ESX hosts where your applications may run. So what this does is creates a large spanning tree failure domain, which also brings scalability problems to your data center. It increases the potential for outages that will impact more and more of the data center, and that's probably not something you want to now extend across multiple data centers either. So that problem gets even worse. I mean, at scale, you're now exposing all of the virtual machine IP and MAC entries to the physical network, which causes more pressure on the underlying hardware. Or you could create compute silos, like we have here with the blue and green networks, only available to certain top of rack switches. Obviously, this is not a great approach either, because it limits your ability to effectively utilize these resources, and you're really tied to one physical location. So with NSX, we've introduced logical switching. So logical switches really enable layer 2 connectivity across a transport network of any IP fabric. And we do this using an overlay technology called VXLAN, which can really span across hosts and physical network boundaries. Logical switches will also span across virtual objects, such as distributed switches and vSphere clusters. So as you can see up here, our networks are now available everywhere our compute environment lives. This really supports VM mobility and enables us to effectively utilize our capacity. Another key point here, though, specific to multi-site, is that these logical switches also leverage the NSX controller. So that the network information gets reported to the NSX controller, allowing it to build up a centralized view of network state. So the state information allows us to remove any dependencies on multicast in the physical network that was previously a requirement with VXLAN. And it also provides us optimizations like ARP suppression. So this is particularly useful in a multi-site deployment. So essentially, we're able to intercept ARP requests that would traditionally need to be broadcast and flooded over our layer 2 network. And we can convert them into control plane queries where we'll ask the controller for all of the virtual machine network information. So the controller will inform us of IP address, MAC address, and actually the hypervisor and VTEP address where the destination virtual machine is running. Then we can use that control plane query information to populate our local VXLAN tables, and now we no longer need to flood that traffic over the network. So this is obviously an important optimization when it comes to multi-site, because we reduce the amount of replicated traffic that needs to traverse a data center interconnect. So logical switching enables and optimizes our layer 2 connectivity across data center boundaries. The next feature is distributed routing. So distributed logical routing also helps address a number of important network challenges. So things like suboptimal traffic flows, where virtual machine to virtual machine traffic may need to traverse multiple levels of the physical network for a routing decision, only to return directly back to another virtual machine at the same hypervisor layer. So our solution here with NSX is to take that centralized routing model and move the default gateway to the network edge within every hypervisor participating in an NSX transport zone. So what that means is virtual machines will see the same virtual MAC address as their default gateway, regardless of which hypervisor they're running on. It also means we're able to make our first hop routing decision directly at the source hypervisor and no longer in a centralized place in the physical network. It's also extremely scalable, so we can support up to 1,000 logical networks on a single distributed logical router instance and 1,200 distributed router instances in an NSX domain. So by moving this routing function into the hypervisor, we also get massive scalability. So in the context of multi-site, what happens here really is that distributed routing enables east-west routing to occur directly at the source. So again, we don't have to traverse that data center interconnect unnecessarily for a routing decision. So our next component here is distributed firewalling. So in a traditional security model, physical firewalls have to be attached to the network, traditionally up here at the aggregation layer of the network, where they'll become a choke point. You need to steer traffic to these centralized firewalls. And not only that, they also have limited context about the application or workload because they're running several wire hops away from that workload. So by the time traffic gets to the firewall, you might either be limited to IP and MAC address-based rules or having to do deep packet inspection, which might have its own overheads as well. And finally, these physical firewalls also have throughput constraints. Once you get to the maximum supported throughput, you have to start trying to cluster and scale out, adding more and more complexity to your environment. So in comparison, the NSX Distributed Firewall provides policy enforcement directly at the hypervisor, and it also gives us additional context. So it has the ability to use information from vCenter to build firewall rules based on objects like virtual machine names, clusters, data centers, networks, all of that rich context that we get. In addition, it also provides us on a hypervisor line rate performance. So another powerful feature here is that we actually scale our firewalling performance in line with our compute performance as well. So when we add a host, we can add potentially up to 20 gigs of additional firewall capacity at the same time. So this is important in a multi-site perspective because being able to apply that policy down at the VNIC level where the workload runs, rather than in a centralized location in the physical network, is really critical. It means that firewall policy follows the virtual machine regardless of location. And again, like the routing, that policy is applied before traffic hits the wire. So it really addresses challenges with firewalls that might be introduced by asymmetric traffic flows. And finally, L2 VPN. It's the final feature of NSX that we're going to cover. It's provided by the NSX Edge Services Gateway. So I'm going to come back to this in a bit more detail. But at a high level, the L2 VPN, what it provides us is an SSL secured layer 2 extension over any IP network. So we run an NSX Edge Gateway in one location as an L2 VPN client, while another edge in a different location and different administrative domain runs as an L2 VPN server. So it provides us the ability to extend any combination of VLAN or VXLAN networks, all with no specialized hardware and leveraging the multi-tenancy available in the platform. So L2 VPN gives us network extension with IP connectivity as the only requirement. All right, so now we're going to, with that background out of the way, kind of jump into the core of our session here, which is really the NSX multi-site deployment options. So what I'm going to do to begin with, I'm going to describe the three NSX for vSphere active-active multi-site deployment models. So our first solution leverages VXLAN with stretch clusters, so vSphere Metro storage clusters, and really supports enterprise use cases where active-active storage is available. So secondly, we also have a deployment option also leveraging VXLAN with separate clusters when active-active storage is not available. And third, there's the L2 VPN-based solution, which can be used to support both cloud and enterprise use cases when a solution needs to extend across separate vCenter servers. So the key points here is that all of these solutions meet the core requirement of providing an optimized layer 2 extension over a layer 3 network that spans more than one site and enables our workload and IP address mobility without the need to stretch the underlying VLANs. So another important point here is that these solutions do support local egress. And by local egress, I mean traffic that exits the data center without going over the data center interconnect. But it does add complexity, and I'll talk about this more in the next slide. Another point that I want to make is that the appropriate deployment model is going to depend on your environment and your requirements. So it's not a case that there's a one-size-fits-all solution. And finally, the reason that I put disaster recovery in a separate section of the session rather than including it here with these three options, is that while NSX can simplify your networking with SRM and DR scenarios, it's not really a use case that requires layer 2 extension. So I think it's important to cover it separately and highlight how it differs from these active-active solutions. All right, so now I'm going to cover my point about local egress and complexity on the previous slide, because I think this is really a critical consideration in multi-site designs. What I always do, my first question is around whether there's a requirement to provide stateful services for traffic entering and exiting the data center. So stateful services are things like load balancers, firewalls, intrusion detection, etc. And if the answer here is yes, then the next question is there really an application level solution to provide local ingress for your applications? So here I'm talking about or referring to traffic that enters the data center from an external network. And given this is really an application or network specific question, in most cases this would be handled outside of NSX. So some of the common approaches that our customers use here are things like network address translation, global server load balancing, Anycast, etc. So, if there is an approach to addressing the requirement for local ingress, then I think a multi-site solution that provides local egress will be a good fit. But if there's no solution in place to this, or it just sounds like additional complexity for limited benefit, then some of the other considerations are really how much bandwidth do you have between your sites compared to the amount of north-south traffic in your environment. And is it a goal to reduce your operational complexity? And one thing I see is that in most cases, the amount of north-south traffic is much lower than the data center interconnect. And funnily enough, people like simple solutions rather than complex ones. So in this case, it may be worth considering a multi-site solution where we have north-south traffic that will actually exit from a primary site and fail over to the secondary site. It's likely to meet a lot of those requirements and provide a simpler solution. And really, essentially, even in that case, importantly, NSX is still optimizing all of your east-west traffic. And given that east-west traffic can comprise up to 80% of the data center traffic, it's really the top priority to optimize. So I am going to come back to this point, but I wanted to raise it early for visibility in the session so it didn't get buried. All right, so now we're going to dive into the details of our first multi-site solution, which is stretch clusters. So I'm going to start by introducing the components and then cover the low-level implementation details over the next few slides. So no surprises, we're going to start with two sites, Site A and Site B, a multi-site with NSX session. And at each site, we deploy compute, network, and storage infrastructure. So note that all of the networks between the sites are layer 3. Also, in this scenario, active-active storage ensures the same data stores are presented and available to both locations. So then we're going to deploy the management components, so our vCenter server, NSX manager, and NSX controllers in Site A, where we'll manage resources across both sites. Then using VXLAN, we create multiple logical switches that provide isolated layer 2 networks spanning over both Site A and Site B. So then the NSX Distributed Logical Router provides our default gateway for all logical switches, and again, spans over both sites. So if we look at some of the traffic flows, let's say virtual machine 1 on the left here wants to communicate with virtual machine 4. It sends traffic to its default gateway, which happens to be the hypervisor that it's running on. Our first hop routing decision is made, and then at that point it's a VXLAN forwarding decision where we will query the NSX controller. It will then tell the source host which hypervisor the destination VM4 is running on, and we'll forward traffic directly to virtual machine 4, all within a local site. Then if we need to communicate, virtual machine 1 needs to communicate with virtual machine 5. Again, routing will occur directly at the source. That hypervisor will be notified by the NSX controller exactly which hypervisor VM5 is running on, and we forward using VXLAN via unicast directly to that destination virtual machine. If we happen to migrate virtual machine 1 over to site B, which we can easily do, the next time it communicates with virtual machine 5, that routing decision will now occur on a hypervisor over in site B, and this traffic will not go over the data center interconnect at all. So you can see how these distributed functions really help optimize our traffic flows in multi-site scenarios. Then finally, what we would do is we will deploy NSX edges. So here, these are going to provide our north-south connectivity, so for traffic that will leave the data center. And so optionally, we can deploy here a gateway at site A. And if we want to optimize our egress traffic, we can optionally deploy a gateway at site B as well. And so in this scenario, for traffic that has to actually go north-south, any virtual machines that are running in site A will use the site A edge gateways. And virtual machines over here in site B will use their local site gateway as well. And we'll talk about exactly how this works over the next few slides. So in terms of the solution detail, obviously this approach requires a supported vSphere Metro storage cluster configuration. This is really what enables our stretch clusters. So all of your standard VMSC design considerations will apply, with NSX really addressing all of your network and security requirements without the need to stretch any of those underlying VLANs and those traditional challenges we talked about. So a Metro storage cluster requires a common storage subsystem that spans both sites, and those data stores need to be accessible from both locations. So really, as a rule, this solution 1 requires high bandwidth and low latency between sites. So some of the examples of this active-active storage would be EMC vPlex, NetApp Metro cluster, etc. There's a range of certified solutions available from all your favorite storage vendors, and we even have a VMware hardware compatibility list specifically for Metro storage clusters. So all those rules apply. So stretch clusters will also support vMotion of workloads between sites. So as we mentioned, our solution here will use layer 3 for all of our VM kernel networks. So management, vMotion, IP storage, all on layer 3 networks. So they don't need to be extended across sites. And another important point, so all of our management components, such as vCenter Server, NSX Manager, and controllers, will be located in site A. At any point in time, they'll always run in the same site. So with the stretch cluster, the latency and bandwidth requirements are typically dictated by the storage vendors. So as an example, with vPlex, they have a requirement to support 10 milliseconds round trip time, which actually happens to align very nicely with the vMotion latency requirements when you have vSphere Enterprise Plus. So that tends to be a target number. Another point here is that the Metro storage clusters enable disaster avoidance. So workloads can be proactively migrated between sites, but it only supplies a basic disaster recovery capability. So this leverages vSphere HA and can automate disaster recovery, but it really does not have the orchestration and testing features that a product like SRM does. So probably another key point that I think people will be wondering about is how do failure scenarios work in this type of a design. So essentially loss of either the NSX controllers or the data center interconnect will only result in a fallback to data plane-based learning. So we're going to use all of the existing cached network state in your hypervisors and the VTEP tables that have already been synchronized to the ESX host. So all you would lose is the benefit of optimizations like ARP suppression, but within that site, while the data center interconnect or the controllers are unavailable, there's no impact to traffic forwarding. Also, while that data center interconnect is down, vCenter Server will not be able to migrate or manage hosts in the remote site, so you won't be migrating workloads or you won't be provisioning new workloads, so your network state will essentially be quite static. So once those controllers and the data center interconnect are then restored, normal operations can resume. So this is a solution that also handles failure scenarios gracefully. Another optimization that's important in these multi-site solutions is that we use hybrid mode for VXLAN replication. So again, this is around optimizing the amount of traffic on your data center interconnect. So hybrid mode allows us to leverage local multicast within a segment, layer 2 multicast or IGMP, and then when we need to go across a segment, we only send one copy of the frame that needs to be replicated to a proxy VTEP in the other location, which is then responsible for re-injecting that into the local segment. So when we need to replicate traffic, we're only sending it once over the data center interconnect. And so this stretch cluster scenario, it's a solution that I'm quite excited about because I see NSX and Metro storage clusters as very complementary technologies that certainly fit a sweet spot for NSX. So, sorry, my clicker's just died. Okay, so now I'm going to cover the cluster detail in our stretch cluster scenario. So as we said, Metro storage cluster enables our stretch clusters across 2 physical sites. In an NSX deployment, all of our clusters will be stretched. And under normal conditions, all of the management components will run active in a single site. So that means that these components, because they're protected by vSphere HA, would automatically be restarted over at site B in the event of a failure. So this, because we're not stretching any networks, and that includes the management network for these virtual machines, because it only exists in one site at a time, there is one step in this recovery process, which is essentially enabling that management network over in site B. So basically, the management VMs can all use exactly the same IP addresses they were using in site A. And so this could be a pre-configured network with, the SVI or layer 3 interface shut down. So it's a simple step of enabling this network over in site B when your management components fail over. So edge gateways will be active either in a single site if you're not concerned about local egress, or in both sites if you are. So in that case, either they'll be failed over to site B, or actually the site B gateways will just take over for all traffic. And as we mentioned, all of the workload clusters are stretched as well. So virtual machines can be vMotion between sites, and they'll automatically be restarted by vSphere HA over in site B in the event of a failure. So you can see we have that automated disaster recovery capability, because the logical networks that back these workloads are already available and spanning both sites. So another Metro storage cluster consideration is that vSphere HA will be configured with multiple isolation addresses. So we'll have a local isolation address and one across the data center interconnect, plus our data store heartbeating. So we're going to make sure that HA only takes action in a true site failure and not just the loss of the data center interconnect. Look, in the interest of time, I'm going to cover this very quickly. But in a stretch cluster environment, managing your DRS settings is really critical. So DRS is really used to balance resource utilization, provide site affinity, improved availability, and also ensure that you have optimal traffic flow by minimizing the amount of intra or inter-tier traffic that needs to traverse your data center interconnect. So it's important to understand your DRS considerations. And we typically use DRS rules that state VMs should run on hosts within their DRS group rather than must. So this allows vSphere HA to take precedence and restart those workloads if required, and make sure that DRS doesn't lock them to a single site. And there's a few configuration examples here on the screen, which really describe how DRS helps keep workloads on the same site for optimal performance. So for example, you might want to keep latency-sensitive applications together on the same site and only fail them over together. So as I said, they're critical. You can use this slide as a reference. I think that's enough about compute and storage, and we'll move on to the really interesting networking details. Maybe I'm a bit biased. So if we look at the NSX configuration, we'll take a look at the logical view here. So this is option 1, because in NSX, where many things, we're also extremely flexible. We give you enable choice, and you get multiple options for everything. But option 1 is really our recommended approach because it leverages the most of your NSX capabilities. So because our clusters are stretched, our VXLAN transport zone spans both sites, and VXLAN logical switches provide layer 2 across the sites. So, there is one requirement on that physical transport network, which is to support a 1600 byte MTU across that layer 3 transport. It's our single network dependency. And then those logical switches span both sites. As we said, the distributed router also spans both sites and means virtual machines always see the same virtual MAC address. So if we move a virtual machine, there'll be no network interruption due to needing to relearn the gateway address. And our first hop routing is always performed locally. If required, what we do here is if we need local egress, what we do, you can see we have a separate uplink network only for site A. So that's connected to a specific edge gateway. And so our ESX hosts in site A actually have the default gateway for the distributed logical router programmed using an init script that points that traffic to this site A gateway. So hosts in site A will actually route all of their default gateway traffic through 192.168.10.1 or our site A gateway. While over in site B, any of the ESX hosts in this site will have their distributed logical router default gateway programmed via 192.168.20.1. So this ensures that any traffic that egresses the data center from site A uses the appropriate edge gateways, and the same for site B. So, so this obviously keeps the north-south traffic off the data center interconnect. But one caveat here is that given that we need to set that gateway using an init script, on the distributed router we cannot enable dynamic routing, or we don't set a default gateway in NSX Manager because we don't want to overwrite that site-specific gateway. Obviously, if you don't have a requirement for local egress, then these requirements go away entirely. And because we don't have, if you're not enabling dynamic routing on the distributed router, you will need, the edges will need a way of routing to these logical networks. And so the easiest way to do that is to program a static route for all of these logical networks. So having a consistent IP addressing will certainly help here as well. And then finally, the NSX Distributed Firewall gives us that policy enforcement regardless of the virtual machine location. So it really removes the need to maintain any network state on those edges for firewalling. So, a key point here is that with NSX, all that really needs to be done here to enable multi-site for a network is to create a logical switch. So we create a logical switch. We'll patch to a logical interface on the distributed logical router, which, as mentioned before, supports up to 1,000 networks. So these are steps that can be easily automated, and it provides you a very simple and scalable approach compared to the traditional methods of delivering stretched networks. Option 2 is another approach for leveraging NSX. I'll try to cover this one briefly because it's not our recommended approach. But basically, we have a transport zone and logical switches that again span both sites. In this case, what we do is we deploy NSX edges at both sites using the same IP addresses. So you'll see they're both using an internal address of 192.168.10.1, and they're connected to the same logical switch. So this is different than the previous slide where the edges were actually on different uplink networks entirely. And what we do here is we actually define layer 2 Ethernet rules in the distributed firewall to block any ARP to the remote gateway using MAC sets. So these MAC sets will actually contain the MAC addresses of the edge gateways in a specific site. So if we look at our first rule, basically we are defining a destination of the site B edge gateway, which is why that's grayed out. And then we're applying this rule to the ESX host in site A. So what this means is that the virtual machines over here, when they ARP, they will only discover the gateway address of, well, the only device that will respond to 192.168.10.1 is the site A gateway. So all traffic will use the local gateway. And then over in site B, we have basically the reverse firewall rules, where we're blocking any VMs in this site from learning about site A's gateway. So traffic here will use the local gateway as well. So this, again, optimized, and actually an important point here, you'll see we're actually using the applied to field in the distributed firewall. So the reason for using this is that the firewall rules here that apply to site A are actually only programmed on the ESX host in site A. So we limit unnecessary processing of firewall rules at the different locations as well. So caveats here are, option 2 here, the key reason is it does not leverage distributed routing. That's really why we recommend option 1. In NSX 6.0, there was a limit of 10 VNICs on an edge firewall, which limited scalability. Actually, in our upcoming 6.1 release, we've removed that limit by enabling VLAN and VXLAN trunking. So technically, that 10 NIC limit no longer applies. But one of the other reasons why option 1 is preferred is that if you do migrate a virtual machine from one site to another, there will be a minor network interruption because you'll need to relearn the MAC address of the other site's gateway. So option 1 is preferred. But really, the reason why you might use this option is if you needed to support vSphere 5.1 for some example. You couldn't leverage distributed logical routing. That's all. So what if you don't have a metro storage cluster implementation? So can you still use logical switching, routing, and firewalling for a multi-site solution with NSX? Well, absolutely you can. So if we look at the deployment model here, really everything looks the same except for the fact that our storage is not stretched and our clusters are not stretched. But we deploy and manage NSX in one site. We have logical networks, so switches and routers that span both locations, and the ability to provide local egress as well. So functionally it is exactly the same. Our logical network view doesn't change. So, while the designs are very similar, there are a couple of important differences. So given that we're not stretching clusters, we don't need to manage DRS rules and groups. So storage is local to a site. So if we wanted to migrate virtual machines, in this case, we would need to use enhanced vMotion. So basically a simultaneous vMotion and storage vMotion, which has its own bandwidth requirements that you need to be aware of. The latency requirements for that enhanced vMotion are also 10 milliseconds round trip time. But what's relevant in this scenario is that the storage platform is not actually dictating our latency here. So if there's a case where you did not have a vMotion requirement, then the key point here is that all you need to comply with is the latency requirement for our NSX control plane traffic. So this is traffic between the NSX controllers and the ESX hosts. And that has a requirement, or our support requirement there is 100 milliseconds. So exactly the same behavior will be seen in terms of loss of any NSX components or the data center interconnect. The solution is resilient there. We'll just lose the ability to provide ARP suppression. Again, hybrid mode is recommended for VXLAN replication. And so in this case, the solution provides disaster avoidance where you have live, well, actually vMotion is always live, so where you have vMotion. But it does not provide disaster recovery. So that's important to note. You could implement a scripted solution for failover using storage replication. And we actually do have customers doing that today, but you lose some of the automation benefits of your stretch cluster. So given we can't leverage vSphere HA with the separate clusters, basically we cannot automatically recover the workloads here. But as I said, it would be possible for us to replicate and recover using a scripted process. So I guess the key point in a stretch cluster scenario is that a full site outage would definitely be more disruptive. But you still get all of the same logical network benefits. Option 1 is entirely unchanged. You use distributed routing. The previous slide applies 100%. There is a minor difference, though, with option 2. And that's because our vCenter objects are not shared. We can actually leverage the distributed firewall rules here with the scope of the data center. So it allows us to optimize our rules. Whereas in the other case, we had to add the ESX hosts within that site directly because that was the one thing that's not shared among sites. Whereas in this case, we actually have vCenter objects that are not shared. But option 2 works exactly the same way. So we don't need to cover that in much more detail. So now going back to the disclaimer, I said that everything I was going to talk about is currently shipping. That's been true. This is actually a future enhancement that we're working on, but I thought it was important to cover just to show some of the enhancements that are possible with the NSX platform. And the idea here is that if we look at sites where you'll have specific ESX hosts on each site, what we're looking to implement here is the idea of a location ID in the NSX manager. So when you prepare your hosts, you'll basically optionally be able to tag a location for that cluster or those hosts. That location information will be stored in NSX manager and also pushed to our NSX controllers. So we'll store the location ID up here in NSX Manager. Then it will be synchronized to the NSX controllers. And this will actually give us the advantage to have per site specific configuration that the controllers will synchronize to the hypervisors. So the idea here is that the controllers will be aware of which hosts are in a specific site, and we can actually push the routing information down from the controller. So there's no need for that init script workaround. Actually, this could give us other flexibility as well. In this case, I'm applying the location ID to a site in a multi-site scenario, obviously. But it could also be used to do other things like rack-specific optimized routing, for example. So this is an enhancement that we're working on. And obviously, once those site-specific routes are programmed, you'll automatically have that local egress optimized routing. So going back to the earlier discussion on, if you wanted to simplify your multi-site deployment, or if you had no requirement for local egress or ingress of north-south traffic, well, NSX can certainly help here as well. So in this case, the solution in this case is that we would deploy an edge gateway that actually has 2 uplink interfaces. So uplink 1 is active over in site A, and is enabled for dynamic routing. So that uplink will connect to the next hop router in site A and form a routing adjacency and advertise all of our logical networks so that all of our north-south traffic will run through site A. The uplink 2 has no connectivity in site A. You can see here it's kind of hanging over to the side uselessly. Then in the event of a failure in site A, the NSX edges can be restarted automatically using vSphere HA in our stretch cluster, or they could be replicated using separate clusters over to site B. And then over in site B, uplink 2 will actually connect to our next hop router, and it's uplink A that is not connected to anything. So we will then, our adjacency here will time out. Site has gone anyway. And will be reformed over in site B over uplink B. So now all of our networks will automatically be re-advertised via site B. So you can see that this is a solution that, while it might not be quite as sexy as a full active-active solution, it's going to be the right approach in the majority of cases. Because if reducing the amount of north-south traffic over your data center interconnect is not a huge problem, and remember that your east-west traffic is already being optimized and is not unnecessarily traversing that data center interconnect, this actually gives you a much simpler solution that can be implemented without any special considerations for your application traffic or your north-south traffic flows. So definitely something to think about. Obviously, we support both models. I'm not saying one is better than the other, but again, it's not a case where one size fits all, and you have the flexibility to implement the right solution for your environment. Okay. Well, I need to speed up a bit, don't I? Okay. L2 VPN. So in this case, as I mentioned, L2 VPN provides an SSL secured extension over any IP network. We kind of covered this, so I'll skip forward. I wanted to briefly cover the enhancements in our 6.1 release, because we've added we've really invested heavily in this feature. So I mentioned the trunk support. So it allows us to trunk multiple internal networks to be extended over an L2 VPN. In the past, we could only extend one network per L2 VPN tunnel. We've also unbundled the L2 VPN client from NSX management. So it means that the solution will actually work without NSX on the client side. And technically, it will even work without vCenter server. So you'll just lose some of the automation benefits. So we're really removing the barrier to adopting L2 VPN. We optionally support egress optimization using layer 2 filtering of the remote gateway. And we can also coexist with an existing gateway device. So basically, the L2 VPN can operate in a layer 2 only mode, meaning a less disruptive deployment model. We have some performance optimizations that help enterprise use cases where we could run with null encryption, for example, as well. And you can try the L2 VPN enhancements in the VMworld hands-on labs. Okay, so I'm going to build these out very briefly. Let's say this is the enterprise use case where we would have NSX at both sites. And in this case, we're actually extending VLANs 100 and 200 on the left side. We're tagging them with tunnel IDs and extending them to VLAN 1000 and 2000 over on the right side. So you can see here we're providing an extension where we can actually map different VLAN IDs if required. We would enable L2 VPN server on one of the edges, in this case site B, L2 VPN client on the other side, and then actually build our tunnel over SSL. So now we're actually extending these networks so that VLAN 100 is actually on the same layer 2 segment as VLAN 1000 and vice versa. So this is the enterprise use case where you might have NSX at both sides. We also support a hybrid cloud option. The big difference here is that the edge is actually deployed in a standalone fashion, layer 2 only. So we again have a trunk interface, but it uplinks to an existing router at your site, at the remote location. In this case, we're actually extending two VLANs here, VLAN 50 and 51, to VXLAN 5000 and 5001 at the service provider site. And again, same thing, we enable L2 VPN client and server and build our SSL tunnel. So this gives us the ability to extend layer 2 independent of vCenter server. All right, very quickly, disaster recovery in a couple of minutes. So SRM, as we know, gives us a classical DR solution with one protected site replicated to a recovery site. So it really enables the ability to recover from a full site failure with automation of the DR runbook. So storage replication is an important component of SRM. It can be done at both the array level or virtual machine level. And data stores and VMs are replicated from the primary site to the recovery site, all standard SRM stuff. Obviously, in the event of a disaster, SRM runs its recovery plan, which also supports changing the network the VMs are connected to at the recovery site, and then powering these workloads on in the order defined by your SRM protection groups. So it also has some other nice features like testing of DR and external scripting hooks. So in a DR solution, you can actually see that there are two vCenter servers here. So one on the left paired with SRM, another one on the right paired with SRM, and separate NSX domains. So they're both operational at the same time. So the difference here is we're not extending the control of one NSX domain. And really, because these DR scenarios don't require workloads to be active in both sites at the same time, but the benefit here is being able to use the same IP addressing, gateways, and security policies at both sites. That's the benefit that NSX provides and network virtualization provides. So in this case, what we need is less of a layer 2 extension and more of an approach to synchronize configuration among these NSX domains. So I'm probably going to have to skip through this, but basically there are a number of standard capabilities that you can leverage with SRM. So the ability to map from one VXLAN logical switch at the primary site to a different logical switch. Then placeholder VMs can already be added into security groups at the secondary site so that they can be protected by the NSX Distributed Firewall. And we can also leverage dynamic routing. So these are out-of-the-box capabilities. Then in terms of things that need some additional integration, well, really what's required here is synchronization of our distributed firewall rule set and security group membership, and also leveraging those hooks that SRM provides, so that when VMs are added into a protection group, we automatically add the placeholder VMs into the correct security groups that are already synchronized. And then obviously if we're leveraging dynamic networks, well, we'll want to synchronize these as well. So this is a process that we've tested and works out of the box. And the integration down here is something that we're validating and we'll be releasing a white paper on. But there's really no reason why you can't start with this immediately. So what this looks like in a bit more detail, or if we take a closer look, you can see here we've got logical switches, distributed routers and edges that exist at both sites. And networks are only advertised via the primary site. So our primary VMs are running in their security groups here on the primary site. Placeholder VMs are running over at the recovery site. So in the event of a site failure, so we lose site A. So what will happen here is the placeholder virtual machines over in the recovery site will become active. So they'll become the primary virtual machines. They will then be automatically protected by the NSX Distributed Firewall. And then at that point, all of our logical networks can actually be re-advertised using dynamic routing. So we can achieve DR in this case without extending networks across both sites. All right, so a very quick summary, and then hopefully I have time for a few questions. So in summary, NSX provides all the required components to implement multi-site solutions for both enterprise and cloud use cases. So we provide a multi-site solution in software that complements our existing products to bring network, compute, and storage together in a solution that's really built for automation, in contrast to hardware-based solutions that only focus on the network and rely on manual device configuration. That NSX and Metro Storage Cluster are complementary solutions, and that we support both single and multi-vCenter use cases. With that, thank you very much, and I will either take questions now or can certainly wait outside and answer any questions you might have as well.